Oh, okey. 7 hari lepas. Saya tanya kelas belum mula. Ingatkan hari ni. Okay guys, so let us continue with this test question. Test 2, 156001 So this is the schematic diagram, and the first case that we are going to look is without using any regenerator. So what we have right here is a T4 equal to T5 because there is no regenerator and T10 does not exist. So this is our TS diagram. Alright. So we need to define all the temperature before we can answer the question 2, 3 and 4. The TS diagram is shown as this, the TS diagram. Okay. So now T1. T1 is given as 30 degrees C. And in this case, T1 is equal to T3. Why T1 is equal to T3? Intercooling. Bukan intercooler. Because of complete intercooling. Yeah. That's why the temperature is the same. The temperature T1 is equal to T3, meaning that is complete intercooling. Okay. So what is our T2? So T2 is equal to T1 P2 over P1. Gamma for air minus 1 divided by gamma for air. And what is our P2 over P1 is equal to 3. Okay. So can someone calculate for us? How much is that? So you are apa? Ya, berapa?
Sir, the gamma is 1.4, right, sir?
The gamma, let me see. The gamma, I think I given you the gamma. No. Okay, the gamma is given as for air, right? Let me write it here. So for air, the Cp is equal to 1.005 and the gamma is equal to 1.4. For gas, the Cp is given as 1.15 and the gamma for gas is equal to 1.15. Okay, so that is your value of Cp and gamma for both air and gas.
I got 414.73, sir.
414.7
Yes.
Kelvin. Okay. Next is the T3. Okay, T3 is equal to T1. How about T4? If you look right here, we are going to get the T4 equal to T2 because we are going to use the same value. This is 30 plus 273. This is also 3. And this is for air. So T4 we get is equal to T2. Okay. Then next we are going to get after T4, we are going to get T6. And T6 is equal to T8, which is a 950. Okay. Right now, the T6 equal to T8. T6 is equal to T8. After 6, we are going to get T7. What is T7? T7 is equal to T6, P7 over P6. But this is gamma for gas, minus 1 divided by gamma for gas. And what is P7 over P6? P7 over P6 is 1 over 3. Okay, because we have here P7 over P6 is 3. Then P7 over P6 is 1 over 3. Given in the question that all the pressure ratio of the both for the compressor, both compressor and both turbine, they are all 3. Right? So we are putting P6 as 950 plus 273 and P7 over P6 is 1 over 3. So how much is that?
I got 1059.73, sir.
10?
59.7.
Oh, yeah. Sorry. You're
Uh,
using the gamma value, how much? The gamma for air?
1.15, sir.
Oh lah, sorry, I think it's wrong right here. It's not 1.15. It should be 1.333.
1.33.
Yeah, it should be 1.33. Sorry for that. This should be 1.333. Too small. Too small, the value. Okay, please calculate that again.
929.5, sir.
9 to 9.5.
Yeah.
Okay. 9 to 9.5 Kelvin. Okay, right. So that is for T7. What is T8 is equal to T6. And how about T9? T9 is equal to, this is also the same, 8 P8 over P9 is 3, then we should get the same value. T9 is also the same as T7. Okay? And in this case, we also have the same as T10. Because right here, T10, we don't use any heat exchanger. Therefore, T9 is equal to T9 is equal to T10. Right here, T10. So T9 is equal to T10 in this case. So just put right here, just take note, is equal to T10. Remember, this is the case without using any generator. So from now, we are getting all the temperature. Okay, all the temperature. Then we try to answer number 3. Whether you want to put it one by one or you want to put all the equation inside one equation, is up to you. So what is our W net? we need the work ratio, meaning that we need to have individual work for the turbine. So it's advisable for you to have each one different calculation. So what is the work for the turbine? Work for the turbine is equal to, we take one work times by 2 because all the value is the same. So this is W67. So this is summation of turbine. This is 2 CPG and then T6 minus T7. So that is for the turbine. And then for the compressor, what is the total work for the compressor? So sigma W compressor again. The work is the same because all the temperatures are the same. So 2W12 is equal to 2 multiplied by CPA T2 minus T1. So how much is that?
For W67, 675.05.
For both.
Yeah. No, sir. Times by 2.
Okay. Sorry. How much again?
For single turbine, 337.53. For both of the turbines, 675.05.
3,
7.53.
both?
675.05. Job again.
Okay. And then for the compressor?
Then for compressor, wait, sir. For single compressor, 112.04.
Both?
For both, 224.07.
Okay. Then we can get our W net. So this minus this. Okay.
Four five zero point nine eight, sir.
Okay. 450.98. 450.98 kilojoule.
Sure.
Okay. So this is our W net in terms of kilojoule over kilogram. And then for the work ratio, so for part 3, work ratio is equal to W net divided by the W gross and the W gross for both of the turbine work. Okay, so how much? W net is 450 divided by this is 675.05.
0.67, sir.
0.67. Give me 4 decimal point.
0.6680. 81, sir. 0.6681.
6681. Okay, thank
Yeah.
you. So that is your work ratio. And next is to get the thermal efficiency. Then we need to get what is the heat input. Number 4. So this is our thermal efficiency. Go to W net divided by the Q in. And our Q in right here equal to the Q in from the first combustion chamber for 6. Okay, Q for 6 plus Q 78. This is equal to CP G T6 minus T4 plus CP G T8 minus T7. Okay, how much is that? If you calculate individually, give me the figures individually. Give me the 4.6 first and then give me the Q78.
For Q46, sir, 812.34. 12.34.
8.34 and then for 78.
From 70, 337.53, sir.
Total
Total 1149.87.
1194
9.87. 1149.87.
or 9.87.
49.87.
Okay. Therefore, the thermal efficiency will be Yeah, what is that? This value divided by this value. The W net divided by Q in.
0.3922.
Percentage.
Sorry, 39.22.
Okay, thank you. Okay, that's it. That is what we have on the thermal efficiency. Okay, for the part whereby we don't have any reheater or the regenerator. Right. So now we go to the second part. Let me take the second part of the question. Same schematic diagram, but we are given the regenerator. So we have to take account the T5 and also the T10. Again, we need to sketch the TS diagram. Okay, let's sketch the TS diagram. This is our overall pressure ratio. This is our intermediate pressure. So what we have right here, this compression process, intercooling, second compression. This is our expansion process, reheat, and this is our line. Okay. So this is 1, 2, 3, 4. This is 6, 7, 8, 9. Then we need to sketch, right? We need to sketch the line or the point of 5 and 10 accordingly, right? So as you know, this is our temperature difference, which we call as A. This is our temperature difference where we call as B. And this point of 5 and 10 should be in between. Okay, let's say that is the point. So this is point 5, state 5. This is state 10. So if I can highlight the process of Q in. This is the process of Q in. Okay, this is the process in the combustion chamber. This is the process in the regenerator. Okay, regenerator. And then this is the process of rejecting heat in the heat exchanger. Okay. So put arrow right here. Direction of process, direction of process, direction of process. So this is our TS diagram. Whereby, as far as the temperature is concerned, we have solved the T1, which is equal to the T3 from part A. And then we have the T2, which is equal to the T4. And then we have the T6 equal to the T8. And we have the T7 equal to T9. So 1, 2, 3, 4, 5, not yet. And then 6, 7, 8, 9, 10. So we need to get the T5. So given right here the thermal ratio, so we are going to use the thermal ratio definition, the increment of air temperature in the regenerator, which is the A. A is T5 minus T4. Then divided by B. B is the available temperature difference. And the maximum available temperature difference, which is T9. Okay, it's T9. This is T9, okay? T9 divided by T4. Okay, so you have to draw back this. This line should be right here. Okay, this is 0.9. Okay, we already have our T4, T4, and T9 thermal ratio. Then from here, we are going to get the T5. Okay, anyone can calculate for me what is T5? Okay, what is T5?
I got 800.8, sir.
Yeah.
I got 800.8 Kelvin.
Okay. So based on this 35, then you can calculate our new WNet, same formula, right? And then we can calculate the work ratio, and we can calculate the thermal efficiency. Just follow what we have done before this, but using the appropriate temperature. I want to show you how to get the number 5. You see, the question asks for the exhaust gas. The exhaust gas, right? Then we need to use the thermal ratio again. And I've shown this formula or the proving how we get the temperature difference T9 minus T10 divided by T9 minus T4. Okay, this is, we look, the temperature, here we use the temperature increment from 4 to 5. Here we are using the temperature decrement of the exhaust gas from 9 to 10 divided by the maximum available temperature ratio. So from here you will get the T10. Like I mentioned before this, the T10 we only solve for T10 or the exhaust gas or the exhaust gas of the plant if the question asks us to get it. Otherwise, we don't need that T10 or the exhaust gas from the plant. Okay? So you complete the solution for this one. Any question? Any question? Okay. If no question, then I want to look at the problem 9.4. I want to sketch the diagram of the schematic and also TS. Can you guys read first the question? Okay. A gas turbine generating set two stages of compression are used with an intercooler between stages. The high pressure turbine drives the high pressure compressor, and the low turbine drives the low pressure compressor and generator. The exhaust from the low pressure turbine passes through a heat exchanger which transfers heat to the air leaving the high pressure compressor. There is a reheat combustion chamber between turbine stages which raises the gas temperature to 600 degrees C, which is also the gas temperature at entry of the high pressure turbine. The overall pressure ratio is 10/1. Each compressor having the same pressure ratio, and the air temperature at entry to the unit is 20 degrees C. The heat exchanger thermal ratio may be taken as 0.7, and the intercooling is complete between compressor stages. Assume isentropic efficiency of 0.8 in both compressor stages and 0.85 for both turbine stages, and that 2% of the work of each turbine is used to overcoming friction, neglecting all losses in pressure, and assuming the velocity change and are negligibly small. Calculate the power and also the cycle efficiency. So how many turbine that we have? We have low pressure turbine and high pressure turbine. Okay, and the high pressure turbine drive the compressor, and low pressure turbine drive the electrical generator and also the low pressure compressor. So how many shafts that we have?
Two.
Two shafts. Okay, two shafts. So we need to sketch the two shafts. So let's say this is the first shaft. And then we have the second shaft. The second shaft, we attach the turbine low pressure, which drive both the compressor, the low pressure compressor, and also the electrical generator. So this is our compressor low pressure. This is our compressor high pressure. This is our turbine high pressure. And this is our turbine low pressure. What is compulsory? The compulsory component is our combustion chamber. Before entering the turbine, we must have a combustion chamber. That's the only place we are going to input the energy into the plant. And then we need to ask ourselves, is there any reheat in between turbine stages? Then we look right here, the temperature, maximum temperature, there is a reheat combustion chamber between turbine stages, raises to 600. So again, right here, we should have another combustion chamber, which reheat the gas before entering the low turbine, low pressure turbine, which is 600. Okay? How about the maximum temperature? Is there any difference between the maximum temperature? So this 600, which is also the gas temperature at entry to the high pressure turbine. So the temperature entering the both turbine having the same value as 600 degrees C. Okay, and then the next question we should ask ourselves is in between the compression process. So if we look right here, is there any intercooler being used? Yes, we can see that there is intercooling process, meaning that this should be in between the compression stages. So we are going to cool it, and it been said that the intercooling is complete. Okay, it's complete, meaning that the entry temperature for each compressor, they are the same. Okay, so we need to put a heat exchanger right here. Sorry. Put a heat exchanger right here. And enter the second compressor. So this is our heat exchanger for intercooling. So this is the purpose of intercooling. And then we have to ask ourselves, is there any regenerator or the exhaust gas being used to heat up the air after exiting the high pressure compressor? So we need to ask ourselves this side. Is there any reheat? Then we can see right here, there is a heat exchanger with thermal ratio of 0.7, and it is been describing that this is going to be, you see, the heat exchanger ratio. Yeah, so the overall pressure ratio is 10. Each compressor having the same pressure ratio, and the air temperature essentially is 20. Sorry, guys. Okay, so we need to put a heat exchanger right here. So this is a heat exchanger entry. Of course, this heat exchanger is going to take the heat from the exhaust gas. So I put another heat exchanger, and this is being used to get the waste heat from the turbine low pressure. So this is our heat exchanger. Okay? Right. Of course, this is our inlet. Outlet, inlet, outlet, inlet, outlet, inlet, outlet, inlet to the generator. This is our exhaust gas ejected from the plant. So let us look how many points that we have, how many temperatures that we have. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Same as what we did for the test 2 question. Okay, but this is much complicated because we have a different pressure ratio for the turbine. So if we have 10 right here, and we have isentropic efficiency, meaning that we have extra 1, 2, 3, and 4. So 10 plus 4, in total, we got to get all the 14 temperature. Okay? Then if we sketch this schematic diagram, the TS diagram, we should be careful with the level of the temperature. So let me put this way. Okay. Let me see, in this case, I don't connect the intermediate pressure of the compressor and also the turbine because there is no info saying that it's equal in terms of pressure ratio. But in previous example, for the test 2 question, it been said that the 4 main component, which are the compressors and the turbine, they have the same pressure ratio. But in this case, there's no description about that. The only thing that is given right here is the compression ratio for the compressor. Meaning that for the compression process, this side, the high pressure compressor and the low pressure compressor, the pressure ratio, they are the same. Then our line should be in the middle, which is the intermediate pressure. Okay? And then we know that complete intercooling. So when complete intercooling, the inlet temperature, they are the same. Okay. Then after that, we have the same isentropic efficiency. So if isentropic efficiency, they are the same, then if we can sketch the first compression process, this is our first compression process. Intercooler. Then we are going to have the same level of compression process. Okay, same level. So this level, they are the same. And then because of the isentropic efficiency, this is isentropic efficiency, and the level of this also should be the same. Okay, they are the same because same pressure ratio, complete intercooling, and same isentropic efficiency. Okay, so if we put right here, this is as 1, this is 2s, okay, 2s, this is 2, this is 3, this is 4s, and this is 4. Then we can write here T1 equal to T3, T2 is equal to T4, and the T4, T2s equal to T4s. Okay? Then next, what we are going to have is this expansion process. We know that the expansion process, the inlet temperature for both turbine, they are the same. So we can put the same level. This is our expansion process for the first turbine, which is the high pressure turbine. We have isentropic efficiency. Again, this is the expansion process, isentropic efficiency. We have the regenerator, meaning that we are going to have, okay, before that, see, this is our level of maximum temperature. This is the temperature increment. So this is should be A, this should be B. Then our state of 5 and 10, let's say it should be in between. Okay, if I put here as 5, I may put right here, this is as 10. About the same level, okay? So, to complete this plan, reheat combustion chamber number 2. So this is 6S, 6, sorry. This is our 7S7. This is 9S9. This is the arrow. This is the process in the combustion chamber number 2. This is expansion at low pressure turbine. Then the heat rejected is being used to heat up the air after the second compressor, which is the high pressure compressor. So the beginning at 9 up to 10. So this is how our TS diagram look like. Hey guys, so try to look how to solve all the temperatures. Look again all the properties given and let us after this put all the numbering of the given properties in the question. Okay, so I think I will leave it up to here, and then next week we are going to have a revision on the reciprocating air compressor. Guys, I think for right now we have 2 assignments, right? Guys?
Yes, sir. We already done 2 assignments.
The first one is for what?
The first class assignment, sir.
Reciprocating air compressor.
Yep.
Compressor. And then the second assignment?
Steam.
Steam. Okay. So the next one I should give you the assignment for this gas turbine plant, because each topic have their own assignment. Okay, so I'll get the question ready and then I will give it to you guys. Okay, so let me take your attendance first before we leave. 4, 2, 3.